Please mute yourself. There is a lot of noise. Hello? I will use your attendance, marking your attendance when you send me a message. So please send me. So just share your names here. So let us begin with it. So can I ask Medha to switch on video? Is it okay? Because when I'm teaching, I would need some audience. I can't just see this screen and talk to you people without any enthusiasm. So I need to see someone. Medha?
Yes, ma'am.
Hello?
Yes, ma'am.
Are you okay?
Yes, ma'am.
All right. Please be on video. Somebody please let me have one or the other options also. So right now, okay, we have one more participant. Let me, one more student. Okay, admitted. So now, so we'll begin from whatever I was telling you yesterday. I have been repeating again. So you are learning a new interaction called as strong interaction or nuclear interaction. In other fields, you only study atomic interactions, that is whatever is responsible at the hydrogen atom level. So it is like in chemistry, you have different kinds of elements and you study their chemical properties only. Similarly, in atomic and condensed matter physics, you will learn only atomic behaviors, and in the sense of there is no nuclear features that are appearing here there. So nuclear physics has some additional course which we need to learn. So we develop our mathematical models and how do we think about what is unknown. That is the whole idea. So let me just start sharing what I have done so far. That is, today I could not complete my slides, but I will continue with my handwritten notes. So I want to present it in some proper form, that is for my own interest. But today I will just talk to you with my class notes also. So essentially, I'm starting with unit 3 of your P304B course, correct? So I have what is known as gamma decay. That is, what is gamma decay and how do we start naming the gamma rays which are coming from the nucleus? I would know that they are coming from the nucleus. Okay, there is somebody else. All right. So now I have, I begin with, can you all hear me? You all hear me? Are you okay? Yeah, fine. So I will just say 1 minute. Okay. So selection rules are nothing but what we used to call as conservation laws. So I will explain it in more detail, but right now you just keep it in your mind that selection rules come from conservation of energy. So now I have this kind of a picture. So where I have two energy levels, I say that this is energy level of a nucleus and another energy level of a nucleus with lesser energy. And when a nucleus makes a transition from one energy level to other energy level, like how electron makes a transition from higher energy level to lower energy level, you get some electromagnetic radiation. You have similarly a nuclear energy level, one level, other level. So we have to understand what is happening here, which I will tell you later on. Right now, we will study what are the conservation laws. Can I give some characteristics to this gamma ray which is coming from nuclear energy level A to nuclear energy level B? That is our whole idea. So what I am saying here is What is conservation of energy? When a nucleus decays by emitting a gamma ray, energy of the gamma ray should be equal to energy difference between the two nuclear energy levels. That is first rule. So there can't be any energy coming from somewhere else. So we say the gamma ray carries the energy EA minus EB. That is, you all accept it. You don't have any confusion about it. But then comes what is called as conservation of angular momentum. So we do designate energy levels. By what is the question? So in atomic physics, you used to denote any energy levels in terms of what is so-called, just give me. So energy levels in atomic physics. So suppose I say there is a atomic energy level, one energy level, other energy level. What do you call it? You have to give some quantum numbers to write the energy levels. In harmonic oscillator, you say I have some quantum number n is equal to 0 is ground state, n is equal to 1 is first excited state, etc. That's how you start your life with. In quantum mechanics, I have to learn energy levels have to be named in terms of their quantum numbers. A free particle also has a quantum number that is given by its position, momentum. Its momentum characterizes it. Momentum is a quantum number because it is eigenvalue of the momentum operator now. So similarly, when you take any bound system, you do have energy levels characterized by its quantum numbers. So I will just take these two energy levels and say in hydrogen atom, I have what is called as N is equal to NLM. They characterize a state. I told you a electron sits in a chair. Its name is NLM. So lowest state is there. And then one more here, say N prime, L prime, M prime, something of that sort. So now suppose I gave energy by some means, electron got excited and it is here. I'm giving you a picture, but there is no electron picture like that. But it has a seat for it. And when it comes down here, it emits a gamma ray. So like that, I should know what is this quantum number corresponding to a energy level. Otherwise, I cannot talk about any such picture. So I don't know what kind of energy levels that I am going to get if I have a nuclear potential. I told you already that I don't know what is nuclear potential. But one thing that I pick here is spin and parities. That is what we call as angular momentum. In nuclear physics, it is called spin. Spin means total angular momentum. I'm not writing it all in my notes. You should know it as some preliminary. Spin is a name for total angular momentum. Of what? Nucleus is characterized by energy levels. Energy levels carry total angular momentum. We call it as spin. And there is another property which I have to highlight here without writing anything. And you should keep it as a story. So energy level is designated by spin. Here I write for energy level A, I have a spin JA. That is my way of writing it. This need not be explained. Everybody takes it for granted that energy level is characterized by spin J. Associated with the energy level A, you have this. Fine. Then I will also say there is some quantity called as parity that is known in nuclear physics. How, you don't ask me, because I'm starting with parity selection rules as such. That's what is in your syllabus. You have to assume certain things. What do you have to assume? I will say parity is a quantum number denoted by pi. It can take values plus or minus 1. One generally doesn't write plus minus 1. 1 is not written. It's either plus or minus. Why? I will tell you later on. But parity is something associated with a nucleus. A nucleus is a quantum system. A quantum system has its spin. We say it has a spin and it has a parity. Why parity? It is these kind of quantum numbers. If you know quantum theory, in quantum theory, what are quantum numbers? So do you have any idea about how do you get these quantum numbers? We solve the Schrodinger equation, stationary state Schrodinger equation, xi is equal to E psi. And then I realize that there are some energy, that is quantum numbers. I may write psi n, whatever, n is some quantum number. So that comes because the Hamiltonian commutes with some quantities. So in addition to energy, you have other quantities appearing. For example, in hydrogen atom, in addition to energy, you have angular momentum of the particle, electron, coming in as a quantum number, because Hamiltonian is commuting with such operators. So we do in quantum mechanics, I can't talk about all the properties of the system. Whichever are commuting, I can talk about it. These are rules of quantum mechanics. This becomes a theory. In quantum theory, I have to know what are commuting. So because I don't even know the Hamiltonian of a nuclear system, I am only telling you in general, angular momentum is a good quantum number, which we will justify as we go ahead. I will right now, I am saying that it has a good quantum number called angular momentum. Thing is, I will ask, does Hamiltonian commute with what is called as parity? What is parity? So if you ask me the question parity, you have learnt it in your quantum mechanics class, but as just like whatever you are saying. So I'm just explaining it, though it is not relevant for your course. You should all have learned quantum mechanics. When I say a level is designated by a quantum number, that's all known to you. I am telling you a nuclear energy level. I will say that it is characterized by a spin and parity. Everybody will continue with such a notion. So I am explaining you in quantum theory. When do I say angular momentum is a good quantum number? It commutes with the Hamiltonian, then it is a good quantum number. Right now, we don't know what is the Hamiltonian, but I will say that it so happens that we have found that nuclear energy levels can be characterized by angular momentum through my experimental indication right now. We don't know, but we assume that spin is a good quantum number. We don't have any justification for it, but let us take that nuclear energy level is characterized by spin. Fine. What is the angle? What is the parity? Parity is some thing which I will just mention it to you. Suppose I am a scientist, I will use a coordinate system. Without a coordinate system, I cannot do anything. I have X, Y, Z as my coordinate system. Suppose somebody else, that is, I am using this coordinate system. Another scientist prefers to use some coordinate system where I have X and Y, fine, but Z comes down like this. It is an orthogonal coordinate system, fine. So I can't write a three-dimensional picture in your scale, but what is minus Z becomes a Z for another scientist. There is no harm. You can choose any coordinate system as long as you can relate one to another. So this is called as a right-handed coordinate system. Not important for your exam, but I am telling you a right-handed coordinate system and a left-handed coordinate system. What are they? There is no difference as far as physics results are concerned. So far, we should take that if somebody uses x, y, z as in a plane, let us say x and y, I use a right-handed kind of anti-clockwise motion from x to y. If I take x to y, a anti-clockwise rotation, then if you turn a screw anti-clockwise using your right hand, then a screw moves upward. If you check it, that is a convention, how people form conventions. If I turn x to y, a screw moves upward. So I will say upward direction here, this direction towards me, and they come from the screen to me. That is the z-axis. They write it like this. Okay. But suppose I have x and y same, but I am turning it using my left hand, that is anti-clockwise. I use an anti-clockwise motion, then z goes downward. But both coordinate systems are valid as far as my coordinate systems are concerned. Left-handed coordinate, somebody is left-handed, somebody is right-handed. I prefer to use that, you prefer to use that, but description of physics will not change. Is the notion that we have. So whenever I have such a notion, I have some operator which takes XYZ to another XYZ of the right-handed to left-handed. We will talk more about it in your elementary particle physics class also. But we generally say right-handed to left-handed transformation. There is a transformation. That transformation is called parity operator. So I use here parity is denoted by a operator pi. And as you know, if you apply parity twice, 2 times on a system, it gives you one identity. Parity once will take left-handed to right-handed, right-handed to left-handed again. So it has eigenvalues plus or minus 1. So anytime if I say physics is unchanged under parity, I will say the Hamiltonian does not know which parity, which right-handed or left-handed I am using. The Hamiltonian does not know. So I will say it commutes with the Hamiltonian. So I write any energy levels with eigenvalues of parity, which are always plus or minus 1. Nothing else. If your harmonic oscillator quantum number n, it can take value 0, 1, 2, 3, etc., etc. But parity is also a quantum number which tells me, can I use right-handed or left-handed system? No, it doesn't matter to you. When I say it doesn't matter to you, there are 2 chairs possible for the system. 2 chairs with one is parity plus, other one is parity minus, because it commutes. In addition to energy, you can talk about spin, you can talk about parity for a nuclear energy level is what I am assuming here. It is possible because it's more general for me. Angular momentum is conserved in many cases, so we take it for granted. So we say that in addition to energy, I can give some quantum numbers even though I don't have a model, even though I don't know what is the force. I will say parity is a good quantum number because always I can choose any coordinate system. It shouldn't matter. Any Hamiltonian that I am going to construct myself, any new Hamiltonian, I assume that it is commutes with the parity. So in general, I will say nuclear energy levels are characterized by spin and parity. So that's what is written here. All that is for you to learn as a story. That is, keep on reminding yourself that we don't know anything, but energy levels should have a quantum number. In nuclear physics, we take spin and parity as the quantum numbers. So that is our beginning. So I have 2 energy levels. I don't know they exist, but I have to use energy levels. So energy levels have a name. Their name is their quantum number. The quantum numbers are Ja pi A, Jb pi B. You should always know that pi is plus or minus. One is plus, minus. So here I may have a plus, down also I may have a plus, or I may have a plus here, I may have a minus here, I may have a minus plus or minus minus. All possibilities are there for any given 2 energy levels. This is just when you try to understand everything. So with such a thing, when there is a transition, I told you there is always a conservation of energy which you accept. What is the energy of the gamma ray? Gamma ray carries a energy which is a difference between the energy levels. It should be equal to the energy difference which is written here. E gamma is equal to EA minus EB. EA is the higher level, EB is the lower level. Having said that, I have to explain what is conservation of angular momentum. If Ja pi A, Jb pi B denote spin and parities of nuclear energy levels A and B, then the emitted gamma ray carries an angular momentum. I denote the angular momentum by L, and for a photon we don't call angular momentum. Gamma ray angular momentum is called multipolarity. So we are introducing new names. The name of the angular momentum carried by the gamma ray is called multipolarity. So if Ja and Jb are angular momenta of 2 energy levels, gamma ray carries a multipolarity L, and L cannot be arbitrary. It cannot be any value that you like it to have. It changes from Ja minus Jb to Ja plus Jb. Ja minus Jb has a modulus because I always say that angular momentum, it's whatever we call angular momentum here, it is a positive number. So I have to again come back to your quantum theory and talk about it. What is angular momentum? You said I will take some angular momentum value. Suppose I have angular momentum. You denote it by j squared and jz. Am I right? These are your quantum operators for angular momentum. Anytime you take angular momentum, why is that important and all that is different story. But if you talk about angular momentum, you should have a mathematical detail of it, little bit of mathematical detail. We define what is angular momentum. J squared is combination of jx squared plus jy squared plus jz squared. Correct? This is called the squared angular momentum operator. Okay, this is what is operator jx squared plus jy squared plus jz squared, or I might have written it as j vector, not notation. Vector doesn't mean what we know as a vector. Three components. I'm bored to write it all the time. Write a vector notation. Nobody will kill you using vectors for operators. So I write j dot j hat. That is jx squared plus jy squared plus jz squared. These are mathematical, some kind of clever use of mathematics that we know with knowing its meaning also. Having written this, I will say that angular momentum does not commute with each other. Jx commutator jy operator wise, what is it? Do you know it? Anybody can answer. Unmute yourself and answer me. What is commutation relationship between angular momentum? If you don't know, I will not feel bad, but you should at least tell me, do you know it or no?
Yes, ma'am.
What is
IH cross JZ.
Minus IH cross
plus
JZ.
IH bar, plus IH bar? That is fine. Plus or minus doesn't matter. It's a convention. So this is what we obtain for angular momentum operators, and cyclically it goes. Jx commutator jy is not zero is the idea. So then we look at, suppose I had taken j squared. Does it commute with its component jx? It does commute. So we know that this is zero, or j squared commutes with all jx, jy and jz. That's all I want to know when I go ahead to detailed solving of angular momentum eigenstates and eigenvalues. This is a first learning. That is, quantum mechanics is different. I want to know x and p do not commute with each other. Don't ask me questions like what is the position as well as its momentum, because they don't commute with each other. So such lessons will tell you, all right, you have to be careful in what commutes with what. Then only I can talk about such quantities. So I will say this square is like a king. King is, he has to be good with all his uh, prajas. So all civilians. So I will say it commutes with jx, jy, jz. All are commuting with j squared. But jx, jy, jz themselves, they fight with each other. They don't commute. So they are fighting with each other. So king has to choose one of the confidants so that he can work along with one of them. So that is what is the theory of angular momentum. I will pick angular momentum j squared, and anything, any one of the components. Conventionally, I choose jz. I call z-axis as the quantization axis. These are names. Names need not be worried too much. One of the components of angular momentum is chosen. Jx and jy are left alone. I construct commuting operators. They do have eigenvalues, eigenvectors of their own. So when I do this kind of a thing, what I obtain is j squared has eigenvalues, j squared has eigenvalues. In numbers, they are denoted by j into j plus 1. That's what is the value that I get. If I do proper mathematical theory, I get this into h bar squared is only a unit kind of a quantity, but this j What are the values taken by J? I want you to tell me. If you don't know mathematical theory of angular momentum, it is fine. You should know that there is a squared angular momentum, J squared. There is one component of angular momentum which I can talk together. A king and one of the civilians which king has chosen. So now what is J? Values of J. Similarly, I have J, Z. These are operators. They have some kind of kiritas on them. So then I have this takes values m into h bar. These are proved in quantum theory in your whatever first semester, second semester. M takes values from minus j plus 1, one step increase, plus etc. etc. plus j. Minus j to plus j, one step increment. But what is the value of j squared eigenvalue j? What are all the values that it can take? Given j squared, I will write what is the value taken by m. Okay, that's what is your quantum mechanics of angular momentum. Can you tell me what is the value taken by angular momentum? J squared eigenvalue j. Anybody? If you don't know, fine, but I will tell you. I am just asking to know if you at least have any vague memory, because I generally know that if you are learning too many things, you tend to forget the content, main content, which you should always remember. Mathematical details will come when you bring in logic and develop it. That is different story. Don't recall any mathematical steps, but the values of angular momentum, which is physical, allowed by quantum theory. Physical means quantum theory explains it. Can I write J is equal to 1 by 4? At least you answer me that. Can I say J is a complex number? If you don't know that, J squared is a positive operator. It is a square operators. It can only have positive eigenvalues. And the values that are chosen here are known. It can be half integer or integer. 0, half, 1, 3 by 2. All these are allowed by angular momentum. And if j is 0, m has to be 0. If j is half, m can be minus half and plus half. This is your angular momentum theory. For me, your angular momentum theory that you should remember always is angular momentum components do not commute, and squared angular momentum can assume values allowed by quantum theory, and our science and our nature obeys it. Quantum particles can have angular momentum 0, half, 1, 3 by 2, etc. And m, angular momentum z component can take values this. This is the result of a mathematical detailed theory, and we have not found any differences from our experiments on this kind of a thing. So now if you recall further, just to remind you, if you write angular momentum only coming by its motion, I write R operator and a P operator. From classical theory, I know R cross P is a angular momentum. We call that as orbital angular momentum because we have, in addition to that, I have something else. You start learning what is this. Even here you have Lx commutator Ly. This is not zero in quantum theory. Classical theory, you learned angular momentum for several reasons. In quantum theory, this is not zero. It is IH bar LZ. If you work out R cross P can be looked at as, if you write what is P, angular momentum, sorry, momentum, that is minus IH bar dou by dou x, dou by dou y, etc. That is, if I am writing only px, it is minus h bar dou by dou x. In other words, if I write a L squared, that is a differential operator involving dou by dou x, dou by dou y, dou by dou z, and xyz. If I simplify it, then I solve what are the eigenvalues of L squared operator, Lz. Why? L is a king, L squared is a king, and one civilian has to be used along with him. I use this. Then I get L into L plus 1 is the eigenvalue. Of course, h bar squared is there because it's angular momentum. That is the eigenvalue of L squared, and Lz will carry a eigenvalue ML H bar. So this is also known to you. But when you do this differential equation method, the values of L, that is only integer. You don't get half integer values at all. You only get L is equal to 0, 1, 2, 3, and your eigenstates on L squared acting on something, they are denoted by spherical harmonic functions. This is a function of theta phi. They are the wave functions of angular momentum. Don't mess up your mind with quantum theory. I am only telling you, when you have commuting operators, you have eigenvalues, eigenfunctions. The eigenfunctions have a well-known name called as spherical harmonics in the case of angular orbital angular momentum. L squared acting on ILM. Sorry, I can't write properly, not like in Word. L squared acting on a YLM function. L squared is a differential equation. Then I will get L into L plus 1 H bar squared into YLM. Sorry, I can't again show it clearly. So I have L squared acting on YLM. That is the eigenfunction. This eigen, when operator acts on eigenfunction, you get some number times the same eigenfunction. So if we write any operator A acting on, say, psi, that is equal to some number times psi, I call this number as eigenvalue, this ket as eigenstate. I am writing it in configuration. This is a function. L is a differential operator, Y is a function. It is equal to some number times YLM. And L value is given by only integer if I use a differential representation. So what do I conclude here? I conclude that orbital motion of a particle, any orbital motion of a particle has an angular momentum, but that is only integer. But if I do mathematics, take Jx, Jy, Jz and write what is the corresponding allowed eigenvalues, eigen vectors for this, I get eigenvalues of J squared, not this one. Eigenvalues of J squared can assume what? I just told you. It can assume the values 0, half, 1, etc. What had I assumed? I said J is light angular momentum. It doesn't commute with each other. Jx, Jy is IH bar Jz. That's all I assumed. I don't think that it is R cross P. I don't use this differential form R cross P for J. Then I will get half value also in addition. So this is mathematics. Should I throw it out is the question. But then people experimentally found that there is this value is also allowed, but it cannot come from orbital motion. Orbital motion will involve R and P, but this is out of it. So what is this? Then we call it as intrinsic spin. By birth, a system has some intrinsic spin that cannot be by orbital motion. It has it already. So we understand mathematics and interpret it and then say spin half is a birthright of a particle. We now today we say that electron is a spin half particle. Electron comes by birth, it has a spin half. Its spin values can be plus half and minus half for its angular momentum Z component. Like that we designate angular momentum. Okay. So we total angular momentum is combination of L plus S. I don't add angular momentum just like this. This is an operator. This is an operator vector. And this is an operator. That is, there are three components each for Lx, Ly, Lz, Sx, Sy, Sz. And adding these two will give you a angular momentum total. If I had done such a thing, I again do my angular momentum theory for J squared and Jz, then I can get integer values as well as half integer values for total angular momentum. This is all studied by you. I don't ask you, I am repeating it from what you have studied. So if I have two angular momenta, J1 and J2 operators. Question now is, what is their total angular momentum, values allowed. So I know J1 can take some values, J2 can take some values. What is total angular momentum? I do all my mathematics, then I get the value of, let us say, J squared is given by J into J plus 1. That is the number which characterizes J. But is it related to J1 and J2? Yes, indeed. So I will say that J1 minus J2, whichever is smaller, I take a modulus, and less than or equal to this J, and this is less than or equal to J1 plus J2. Remember, J1, J2 are positive. J squared eigenvalues are positive. J1 minus J2 can be negative, but I am taking a modulus here because that is what I get from my mathematics. So this is what is called as addition of two angular momenta. L and S combined. Any two angular momenta, it's not simply like 1 plus 1 is equal to 2. 1 plus 1, J1 plus J2 can give you values running from J1 minus J2 to J1 plus J2. This is result of angular momentum. This much you should know whenever we go ahead. We don't ask you derive it and all that. You have learned it. We take it for granted that you have learned it. But at least you should know that we are writing eigenvalues and eigenvectors for J squared and Jz. If it contains constituents J1 and J2, what are the allowed values for this J? J can take not just one value. It is not J1 plus J2 alone. It will vary from J1 minus J2 to J1 plus J2. Now, I don't ask you anything. Let me say J1 is equal to some value, allowed value. Allowed value can be half. I told you J can take value 0, half, 1, etc. Now I will take J2. J2 is, let us say, 3 by 2. That's allowed. Half plus 1 is 3 by 2. One step you can increase. 0, half, half plus half 1, 1 plus half 3 by 2, 3 by 2 plus half. You keep on adding half, all are allowed values of angular momentum. Every system is characterized by one value of, let us say, total angular momentum. Quantum state is characterized by one given value of angular momentum. I am taking half for one. Another one is 3 by 2. What is the allowed value of addition of these two? If I add these two, what are the values allowed? So you have to simply do algebra now. Is it one value? I told you J1 minus J2 to J1 plus J2. I'm asking you to use it because I don't want you to sleep off in the class. So tell me answers. What is the allowed value of J? Given J1 is half, J2 is 3 by 2. Is it one value? Is it two values? Is it three values? You should be able to tell me now. Meda?
1.
3 by 2 minus 1, 1. That is
1,
modulus.
ma'am. 1 and 2, ma'am.
Half plus 3 by 2 is 2. These two are allowed values. J can assume values 1 as well as 2. So suppose I say I have written here not half, but I will write, let us say, 0. Now, what is the value of J in that case? You have to learn this, so I am telling you.
1, ma'am.
Not for third semester exam, but you should know this. What is the value? 1 or 2 or 3 or whatever?
1, ma'am.
Only one value, and it is 3 by 2. So fine. So now I will write another one. J1 is equal to 2. I will say J1 is 2. So now tell me. Hello? Anybody else?
2 values again.
2 minus 3 by 2 modulus.
It can assume two values, ma'am.
Tell me values.
7 by 2 and 1 by 2, ma'am.
7 No, you have to say J1 minus J2. What is the value? Modulus J1 minus J2. You tell me.
1 by 2, ma'am.
Half. Okay.
J1
So now
minus
first you
J2
only
is 1
tell
by
me
2.
what are the values minimum and maximum. First write minimum and maximum. Okay. What is the maximum value? 7 by 2. Okay. In between, you have to keep adding 1. In steps of 1, it increases. Okay. I wrote an inequality J1 minus J2 to J1 plus J2. I didn't say only 2 values. So half 3 by 2 is there. Half plus 1 is 3 by 2. Learn the algebra. Mathematics details of the derivation are taken for granted. J1 minus J2 to J1 plus J2. You have to add one step so that you will reach the highest value. 3 by 2 plus 1 gives you 5 by 2.
5 by 2.
4 values are possible here. Okay. That's what is the idea. So now I will again one more because I have to make it little more clear. I will take 2 values which both are half integer. I will say I have a 3 by 2 here. I will take a 9 by 2. Half integer means there is a 2 in the denominator. It cannot divide it fully properly. So now tell me, what is minimum value? What is maximum value? Minimum, smallest value.
3.
Okay. Highest value?
6.
Okay. So you will fill it. 4,
4,
5,
5.
6. So you should know one thing. Whenever J1 and J2 are half integral values, the J value, total angular momentum, is going to be integer only. You can do any circus, you will not get half integer values. If both are half integers, you will get the values of J to be only integer. This is what I'm telling you because you can do it on your own. Follow the rule, keep on trying. So this is what quantum theory tells you. Now apply it to the physics that we are going to talk about. Okay. So that is what we have to do. So now I will tell you what were we talking about. I told you every energy level of a nucleus is characterized by its spin and its parity. And the gamma ray, it has to be given some names. Name of the gamma ray which is coming between 2 energy levels is called multipolarity. Multipolarity of the gamma ray is coming from Ja minus Jb to Ja plus Jb. Suppose I tell you nuclear energy angular momentum is always half integral. It cannot be even integral. Let us say. Suppose I say it is only half integral. If I tell you that, or it is only integer. Difference between 2 integers is an integer, correct? Ja minus Jb, both are integers, it's always integer. If Ja and Jb both are half integer, then also you will get an integer. So I am telling you without assuming too much, but using angular momentum theory that nuclear values of spin, it can either be integer, both are integer, or both are half integer. That is the way nature has designed our nucleus. So if it is both integer or both half integer, then the multipolarity value that I have is going to be given by it's an integer and it's positive, as I showed you already. Difference between Ja minus Jb modulus to Ja plus Jb. It's like angular momentum of a third quantity here. Don't mess up everything and get confused. I am just saying there are 3 angular momenta, Ja, Jb and L. How are they related? I will say it is related by, this is like a triangular rule. If you want to know, given L and Ja, you can find what is the angular momentum of Jb, which turn it around. This is the same rule that is to be followed. J1, J2, J3. J1 minus J2 should be J3 kind of thing. So you can check all those things in angular momentum. Right now, I have 2 spin values. Suppose I take 2 spin values for upper level and the lower level. Then the gamma ray carries, always it should carry angular momentum which lies between J1 minus Jb to J1 plus Jb. It's a rule. I am telling you rules. I am giving you some indications how one would have come towards these rules. It's not just arbitrarily formulated. It follows from angular momentum conservation. So, but follow it as a rule now. You should know how to work out this kind of angular momenta or multipolarity of the gamma ray. That's what is important for us. So I will just go ahead. This is a detailed one now. So now I will tell you, suppose I have parity and nuclear energy levels carry a angular momentum, nuclear energy levels carry a parity. Is there a parity for the gamma ray? Yes, there is one. Without explaining how it came, I cannot explain this, so I will not even give you any hints on that, but I will say based on parities pi A and pi B, what are the values of these parities? Pi A and pi B, what are the values allowed for pi A and pi B? Can you tell me? It's only plus or minus. Remember that. Okay. It's only plus or minus. So either plus or minus is the value of parity. I told you today, I am again making you to repeat it. You know that it is plus or minus. So now, depending on the parity values pi A, pi B of nuclear energy levels A and B, the emitted gamma ray is classified into two types. I am giving you rules. So names are just namesake, you have to take it. One kind of a gamma ray, if I find the gamma ray properties, I will call it electric multipole type and denote it by EL. We need symbols to denote it. A gamma ray coming from a nuclear energy level is called electric multipole type if its angular momentum multipole value is L and it is electric. What is electric? I will explain. There are two types of gamma rays depending on what is called as parity of the gamma ray. So I am just naming it. Parity of gamma ray is very confusing. You can't understand it. Right now, take it as a quantum number of the gamma ray. Gamma ray has a quantum number which is multipolarity. Gamma ray has a quantum number which is parity. Because nuclear energy levels have a parity, gamma ray has to have its parity. What is the parity? So there are types, electric multipole type and magnetic multipole type. And I will just tell you what is the electric multipole type. The electric multipole type is, it is written as electric type gamma radiation. It carries a multipolarity L and is characterized by its parity value. That is, if pi A into pi B, I know nuclear parities. Nuclear parity is pi A into pi B. I will call it as delta pi. Again, a notation. No need for worrying about why. How do I write delta pi as pi A into pi B? Its definition. Call delta pi, write a short name, and it is pi A into pi B. Now, if I take L value, gamma ray has a L value. If the gamma ray L value minus 1 to the power of L, what is the value of minus 1 to the power of L? Given that L is an integer, now you should know, if I say L is an integer, integer means it can be 1, it can be 2, it can be 3. If L is equal to 1, what is minus 1 power L? I'm asking, just are you following? This looks very technical, but once you substitute, you know to solve it. Suppose I say L value of multipolarity is 1. Then what is minus 1 power L? Are you with me or no? That's what I'm checking.
Yes, ma'am. Minus 1.
It is minus 1. Parity can be minus 1. If you take pi A and pi B, multiply them, it is either plus or minus. So is it pi A into pi B is equal to minus 1 power L? If it is so, I call it electric type gamma radiation. If pi A into pi B is not minus 1 power L, but it is, if it is minus here, minus 1 power L plus 1. If L is equal to 1, what is minus 1 power L plus 1? It is plus. Minus 1 power 2, it is plus. I can only have plus or minus. Pi A into pi B is plus and it is equal to minus 1 power L. I have to relate nuclear property with gamma ray property. Then only I can do it. So nuclear property is here, pi A into pi B, and gamma ray property is here. This is a rule. You have to check this and tell me, do you have an electric type multipole radiation? Gamma ray that is coming out of a nucleus. I have to name it now. Naming ceremony is it an electric type multipole or a magnetic type multipole? You will be able to tell me depending on whether pi A, pi B, J A, JB are given to you, you will be able to tell me. So that is what is the first lesson to us. In a gamma ray, it's not arbitrary. So far we used to call a gamma ray is emitted and story ends there. Ooh, somebody is coming in now. All right. So I have gamma ray which is either this or that, both are possible. So let us take an example here again. So I have an example. If L is equal to 1 and I tell you delta pi, pi a into pi b is minus 1. Let us say pi a is equal to pi b is equal to minus 1. What is the gamma ray coming there? I am telling you that it has a multipolarity value 1 and nuclear pi a pi b is equal to minus 1. I know minus 1 to the power 1 is minus 1. So we say the radiation is E1, electric type. L is equal to 1 radiation. Again, one more name is being introduced. The name is electric. L is equal to 1 is called a dipole. L is equal to 2 is called a quadrupole. L is equal to 3 is called a octopole. That is the name used here. We use a name what we tell you. So L is equal to 1 is called a dipole. So we call that radiation which is emitted from delta pi a pi b is equal to minus 1 and let us say L is equal to 1, we say such a thing as electric dipole radiation. And on the other hand, if I have delta pi is equal to plus 1, then we say the gamma ray coming out is not electric type, it is a magnetic type by dipole radiation. So this is an example of whatever I have told you so far. So let us just, that's all I have prepared today, because it is the introduction itself is little important. So what did we say? I just said I have selection rules that one should know. And a selection rule is, if I have a energy of the gamma ray, it cannot be anything that you like. A nucleus emits all kinds of gamma rays. No, it depends on the energy between two energy levels. E gamma is equal to EA minus EB. This is like all other transitions. Fine. And a conservation of angular momentum tells you that a gamma ray carries something called as multipolarity. And what is that multipolarity? It's a theoretical number that I have assigned. That number can only take positive integers. L varies from JA minus JB to JA plus JB, where JA and JB are spins of the nuclear energy levels. That's the conclusion. But you should know all that I told you as your preliminaries. That just in the sense you have to have a logical connection between what you have learned earlier and when you talk about values, allowed values. It is like when I am talking about my students, I can't bring in some kind of flowers and leaves and all that. So I have to talk about students only. So same way here, when I am talking about angular momentum, it can only assume values, integers and half integers. Nothing else is allowed for them. So multiple values, it is only this kind of a quantity that can come. It is a positive integer. So, and then I said parity. I explained you what is parity. And I said, we define gamma ray. If the gamma ray has a parity, depending on nuclear energy levels, that is nuclear parity is equal to minus 1 power L. This is property of the gamma ray. But this is property of a nucleus. They should be related to each other. If this is related in one way, it's plus whatever it is, then I will say it's electric type multipole. Magnetic type multipole satisfies another property. So we have examples for this. This is also there in your general theory. General theory also gives you selection rules, but this itself is enough. Whatever way it is taught, there are many ways many people teach, but this itself is enough for you in the general class also. So we do have to have some problems learning about what is multipole radiation and how do we do it. Next questions that come here is, I am allotting these kind of numbers here. Can I find experimentally if a gamma ray has a multipolarity L? Yes, you do study that in your theory. You do study that electromagnetic radiation carries a multipole value. I will tell you how do you get that L value coming naturally to you. That is a detailed discussion. Multipolarity of angular momentum and what is the parity. Electric and magnetic type comes as polarization of the radiation. Electromagnetic radiation has both multipolarity and as its polarization. Both can be detected experimentally. That is the next story. It goes into details. Right now we are telling you what are important: angular momentum, multipolarity, parity, and two classifications. That's all are there in today's class, and we can continue further with other things. So I can just stop it here. Books. Actually, I write these things myself. I will tell you whenever you need. I will tell you there are some books which I had told you yesterday. So I had shown it to you. Let me just try to show it again. Do I have it here? No. Okay. Mhm. All right. So you have, I am talking to you about electromagnetic. Do you see this? You don't see it. Okay, I will take it out. All right. So now, no, I think I have done some error here. Let me try it again. No? What is it that I'm doing? Try it. Check. All right. It's already time for you. I will stop it. All right. So you have the third unit, which is gamma ray decay in nucleus selection rules. So then transverse electric, transverse magnetic solutions. So this is what I will start from next class. And then all these things are continuing further. So all this discusses about what I told you today as a first class, in the first class. Electric type, magnetic type appear. How do they appear? How do you discuss about, how do you understand it experimentally and all such things? And oh, one or the other mistakes anyway. So books wise, I had told you. Okay. So this is IU. This book also has little bit, it's very complicated. Rai and Nigam. So I don't like it, but that too has this particular part. And other thing is in Platt and Wiskoff. Wiskoff was one scientist who had worked on this. So theoretical nuclear physics, Blatt and Wiskoff has this part. And some of the students of last year batch, they had given me a e-copy of this book. So I can also share it with you. So any other questions, anything else in general, not about this syllabus? So nothing. All right. I have to tell you one thing. Coming Monday, I have an exam duty. I have exam duty for your fourth semester exams. So I will not be able to take your class at 2 o'clock on Monday. So I will engage your class from 4 to 5. That is, there is a slot kept only for that such special things. There is no class at 2 to 3 coming Monday, only next Monday. So I will take your class from 4 to 5 coming Monday. This Friday, I will take general class as usual. Okay. So if there is anything else, you tell me, you can message me in your chat box and all that. That is fine. Anything else? You have a class, enhancers class is there today, right? What time?
4 to 5, ma'am.
Okay, fine. All right. I hope you understood what I said. So we'll go with the same pace, but you should be able to connect to me logically. That's what I expect you to do. Okay. Anyway, all the best. Bye.